Good morning, everyone. So first of all, apologize for the delay, so these things happen. Second, apologize for my voice. This is not my usual voice, so I've been with a cold the whole week, so I hope that I'm still understandable and that you can still hear me. Before starting, I would just like to put a disclaimer. So this talk is structured about giving facts and myths around deep learning. They are just facts, so it's very simple talk. No maths behind. Well, behind yes, but not in the slides. Only general concepts, surface facts. They are quick, a few. There could be many more, and they are in general about deep learning or machine learning. Depends. Can I remove this cursor somehow? And of course, some of them may be opinionated. It's my opinion, and some of the work I will show is done also with the help of the colleagues in the lab working in deep learning. This is not the whole lab. This is only the people who works at some point with deep learning. Okay, so as I said, I will bring here 8 facts and 4 myths, and the reason why I do that is because when I was learning deep learning, they were very enlightening to me. So, and I hope that they are also enlightening to you, and also hope that they make you think about it a little bit. Or if you want, after that we can discuss. It's going to be short, so I guess we will have time for discussion more than questions. So, the first fact: why are these models interesting? Or why there is so many hype around deep learning. The first fact I would put here is because they are accurate, they work. And importantly, they work in fields where machine learning traditionally was doomed to failure or was not performing at its best, let's say. No? Some of these fields are text processing, audio signal processing, image processing, or time series in general. Let's take one example. So, for example, let's take the ImageNet competition. I don't know if you are familiar with it. So, it's a competition about image classification. So, basically, you have several categories of images and millions of them. You train a classifier, and then you want the classifier to predict which is the correct label for the image. So, if we plot the accuracy on this contest across time, we see that the introduction of convolutional neural networks really made a difference in 2012. And since then, the accuracy has only jumped and jumped and jumped and jumped till the levels of human performance. So, second fact and second reason why these models are interesting is that we can start forgetting about feature engineering. So, traditionally, in these type of tasks, they heavily relied on handmade features, handcrafted features. And in fact, most of the time was spent on extracting the features and not on the classification per se, right? Or sometimes you could create kind of a mixture between a classifier that kind of extracts features, but that was really rare in like 5 years ago, 10 years ago. So nowadays, these models allow you to extract the features directly. You can train them to extract the best set of features for your task. Okay. So regarding this, we did a quick experiment at the lab. So we took 2 interns, Guillermo and Susa, and we put them with a toy task, like predicting the success of a call that the telemarketing operator does, based on the logs of the user. Okay. So we record some logs at the company, like time of the call, who you call, all this information, where you are. In order to give you service, we need to direct the call to where you are, of course, and several other things. And we had a feature extractor at the house, was the result of the work of several experts. I have put here months, but I could have put here years. I mean, they don't work all the time on that, so I mean, let's put months. So one of the interns was using this feature extractor and then some classical classification engine. The other intern was using an RNN, a recurrent neural network, with the raw data, with the raw logs. So the result, after 1 month of really working on that, because they had to spend some time familiarizing with the data, etc., etc. So the result after 1 month is the one you can see here, so same accuracy. So basically, if you compare the development time of the 2 systems, that talks by itself, right? So for us, this was a point of no return. So when we did this toy experiment, I guess in the lab nobody now thinks of using XGBoost or other features. Just plain data and a neural network. So the third fact, I've borrowed it from Andrew Wang's book. And we have seen it in the lab. I don't have a specific example, but we often see it. So traditional algorithms like logistic regression scale poorly with data. So you get an accuracy, add more data, you just get a tiny improvement. You add more data, you just get a tiny improvement, etc. In fact, it's logical. So you don't increment the number of parameters of the model. So given the same number of parameters, the more data you add, it's not going to change the statistics of the parameter. With neural networks and the capacity of adding layers or more parameters or different configurations, we observe this phenomenon. So that given adding more data and more data and more data, we still get more performance, more performance, more performance. The other fact is related to the complexity of the algorithms or let's say, the standardization of the process. So before, here you have an audio analysis paper, and this is just the part explaining how features were extracted. So you can see here 1, 2, 3, 4, 5, 6, 7 pages, just devoted to explaining how to correctly extract a huge set of features. So conversely, now what we have could be something like this: 3 lines with 1, 2, 3, 4, 5, 6, 7 numbers. And that's it. And in fact, these systems may perform equally the same for a classification task. This of course, has a lot of benefits. First, code maintenance. So the algorithms are much more standard. Everyone understands what happens there. Less bug prone. So code that is it's much shorter, more easy to spot the bug, and countless of advantages from my point of view. Another interesting thing about deep learning is that you can do transfer learning. So let's say you can have a task like digit recognition, the typical MNIST task, and you can extract some features to solve this task. So these are what you have here in the right. And then maybe you can use the same extraction engine to address another task, which is somehow related to the original task. So let's say now character classification with the same features. Probably you are better if you add this knowledge than if not. So regarding this, we also did an experiment in the house. So Carlos and Jordi, former students from here, applied convolutional neural networks to raw audio in a simple task. So they had a data. They wanted to predict customer satisfaction when they call the call center automatically, but they didn't have a big data set for that. But instead, they had a big data set for conflict. So they had a database of speech labeled with the conflict level. And they trained this convolutional neural network, which you see the architecture here, to detect conflict in that database. And then what they did was just to remove the last 2 layers of the network, put 2 new ones, and retrain, freezing the rest, and retrain for the customer satisfaction dataset, which was much smaller. And they were getting very good accuracies with that. So basically, they were transferring all the features extracted up to here to the new task. Another big advantage of these models is their flexibility. So as you may have seen during this course, they are built of small building blocks that you chain and you tile and you arrange in several ways. And it's up to your imagination and the characteristics of the problem you're addressing on how you connect these modules, right? Which makes all these things really, really flexible. So you can address problems with multiple inputs, multimodal problems with multiple outputs. You can combine different features extracted from different things. And when I say features, I mean other networks, etc. So a very mind-blowing fact is that thanks to this performance and all these advantages, we start learning tasks that were thought to be unlearnable. So for instance, sorting a list of numbers. I mean, this can be done with many algorithms, of course, you know that, But now can be done learning by example. What I mean by learning by example is that you show examples and you say, look, this is ordered, this is not ordered, this is sorted, this is not sorted, etc. And the algorithm learns to sort. Small lists for the moment, but everything will arrive. Not only that, but you can learn tasks from example, again, like performing arithmetical operations from images, or solving the traveling salesman problem, just example by example. So, I mean, I don't know if this sounds great to you, but for me it did. So if you know the current or the state-of-the-art algorithms to solve the traveling salesman problem, they are highly heuristic, based on combinatorial optimization, really hard. So if you can do it example by example, that's great. And many other tasks, simplify mathematical expressions, we see papers now and then, execute code, etc. If you couple these algorithms with reinforcement learning, you can even learn how to play games. So in this Atari game, I don't know if maybe here I'm revealing a little bit my age, but so if you know this game, so you just need to break all the bricks, right? So and and this algorithm basically what exploits is a reward function. In this reward function, what they do is just try to optimize the score. So the more bricks you break, given the less time or the less interactions with the ball, right? So after 600 epochs, I think is it. So the algorithm learns how to pass the ball through the tunnel so that with less effort it gets more points. So, and this is again example by example with this reinforcement learning function. Another attractive thing of these algorithms is that they are generative. So this is not new. There are many generative algorithms in machine learning, but if you couple the flexibility with building blocks, with generative, with multimodality, etc., you can get pretty cool things like this. So here in this example, you are morphing a video, real video, with Kandinsky style painting, and you get a Kandinsky style video, right, generated. So in the lab, we have experimented with generating text, for example. So we have an European project about cyberbullying, and what we first did was just get a lot of we have chats for this League of Legends game where people really well, let's say they misbehave, right? So we took all these chats, which are in fact labeled by a moderator, so that someone misbehaved there. So and trained character-based RNN to generate text with some tweaks. And then we used this char-RNN to just generate angry chats or hateful chats from scratch, and passed these chats to an expert gamer. And many of them, he couldn't distinguish them from the truth. So, for example, here, and why do we train from scratch this tool? Because it's a specific language, so and it's a specific things that are set. So, for example, here you say bot. So bot means bottom of the map. So this player, by the way, this is fuck. So this is artificial, right? So but in fact, Tariq is complaining to another player, to Katarina, saying, "Why did you go to the bottom of the map?" And Katarina says, "Because I can do it." And then another player jumps and says, "No, you didn't have to." The other is laughing, and then they start swearing. Okay, because that's how we train the algorithm, right? To train. To reproduce this type of interactions in, let's say, in these chats. Okay, time for the myths now. So first myth, the deep models are not models of the brain. So even though in the 50s when neural networks were invented, they draw inspiration from very loose, basic mathematical model of the brain. Nowadays, I personally believe that nothing resembles the brain. So it's only a lot of mathematical constructs, basically what we have. So if you hear in the media all these claims that now we are modeling the brain, etc., so I think it's not correct. So the second myth is that these models are data hungry. So they require a lot of data to be trained and to perform nice. And yes, I agree, this is true, most of the cases. But this shouldn't stop you to use them, because in many cases you can still get very nice performances with small data, let's say. One example, so why do they require a lot of data? Well, maybe this is obvious to you now that you have done the course. But basically, so given if the model has like n parameters, you need much more than n points to estimate it. Otherwise, you incur the risk of doing an error like this, no? So in the lab, we did this experiment. So we were studying crowd flow mobility, and we had very few data for that. Not because we don't have users, but because the number of towers in a city or in a geographical area, which is the location of the users, is limited. So for example, in Barcelona, you can have 2,000 towers at most. Therefore, this gives you an idea of the scale of our problem, 2,000 instances. And still, we were able to model it thanks to, and by adding layers, we were getting less and less error. Which was the trick used here? Two tricks: dropout and data augmentation. But thanks to these tricks nowadays, you don't need to be afraid of using these models even when you have low data. It's only that it's a kind of different league. You need to play in a different field, right? And it's not always the case. Sometimes a very handcrafted feature is going to kill your algorithm, of course. If it's very handcrafted and you have it, use it. But when you start from zero and you don't have the feature, probably it's not a bad idea to start with this. And about data augmentation, so here we didn't use deep learning, but we were using data augmentation. And since the purpose of the seminar was about speech, I thought this was relevant. So here we try to predict if you have Parkinson's or not from speech, right? And especially we focus on situations where there is environmental noise or some background noise. And so this has not been studied, so all the algorithms report accuracies with no noise, and they are very nice, 80-something, 90%, some of them. But when you add noise, the thing is that it's not that nice. It drops down to 66% accuracy, very close to the random baseline, which is 50. Moreover, if the noise is mismatched, you get basically random guess. So, and what did we do in this publication to appear in ICASP next month? What did we do to try to address this mismatched noise problem was data augmentation with generating artificial noise and training still a conventional classifier, because that was the algorithm that was used until now to do this type of Parkinson's detection. But the data augmentation helped us go back to the accuracy of matched noise, in the case where in reality the noise was mismatched. Let's say there was noise about a car, but you trained with cafeteria noise or hospital noise, etc. Another myth is that these methods are very hard to understand, their decisions are very hard to explain. So here the point I want to make is that this is changing very fast. So especially there has been a lot of work regarding attention models, which can basically, is what you see in the upper part of the slide. They basically can highlight the zone of the image from which they base their decision. And furthermore, this is another work here, the last one. I find this very enlightening. So this is a paradigm shift in the problem of explaining the predictions of a classifier from my point of view. So basically what they do is that they take the classifier as a black box, and then they basically try to generate or develop a new algorithm to make sense of the predictions. And I think this will be the future. So there will be one algorithm which is specialized in doing things well, and another algorithm, a different box, that will take only inputs and outputs, and will try to make sense of these predictions, and will try to explain to a user or a practitioner these predictions. And that's what they do in this figure in the top left corner. So basically they have an image, and with this algorithm that is not part of the original classification, tagging in this case algorithm, They explain which parts of the image correspond to every tag. There are many other things you can play in order to grasp a little bit and understand a little bit these algorithms. There is this web interface where you can just change the architecture of the network and see how the predictions change. You can look at some representations after some convolutional layers. You can see where every neuron activates or not in a text. These things are changing really fast, and I hope that in the future the scenario will be way better. Finally, the last myth, and having seen all this presentation, you may wonder, okay, is deep learning the answer to everything? Should I forget about the rest? The answer is, okay, no. So remember of the free lunch theorem. And if we look, for example, at Kaggle competitions, it's this table that maybe you cannot see here. But so Kaggle is a platform where there publish some contests and machine learning contests. So and participants need to get the best accuracy in that contest, right? So if we look at the winners of the most of some competitions, we see that most of the time is using traditional feature engineering still, or combining feature engineering and some deep learning models. And sometimes deep learning models is the answer. So, but it highly depends, especially when all these people optimize model ensembles, big models, and etc. Also, when you want to use deep learning in your everyday life, you have to account for other variables. No? So training and deployment time. So maybe the requirement for the client implies that you don't have 24 hours for training or for retraining. So maybe you need to rethink. Complexity and maintenance. This may be a point of neural networks or not, depending on who has to do the maintenance of the code. Sometimes, if the accuracy is a little bit less, but the model is much, much simpler, you apply Occam's razor and forget about the complex model. Or still, in unsupervised learning, I would say the field is not fully developed, so you may still work with previous algorithms. And that's it. So I think it's okay.
Okay, so explain one.